Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host Sean Carroll. I wanted to express my appreciation for those of you who have stuck with it this far. I know that the last three videos in particular, a series building up some fundamental ideas from quantum field theory, they can get pretty abstract. They can get pretty challenging, not because they're intrinsically hard, but because they're very different from what we're usually used to, either in our everyday lives or even in our first elementary physics courses, okay? So I thought we would get a little break today, a little bit of a palate cleanser. There's some big ideas in here, absolutely, but I wanted something a little bit more tangible that we could sort of relate to things we're familiar with. So today's big idea is scale. This is a very big idea indeed, but it is no less profound, as we will see, than the other ideas. Scale is just the size of things, and in particular you might ask, how different sizes of things depend on other variables. If you change one thing, how do other things scale with them is a question that we often ask. We've already talked about this, of course, a little bit, especially in the last video, in renormalization. We talked about the fact that you could put an ultraviolet cutoff in your quantum field theory, and that sort of sets a scale, an energy or a wavelength scale, beyond which you say, we don't know what's going on. We don't know what the laws of physics are. And Ken Wilson and others figured out ways to nevertheless do physics below those energies without knowing physics above those energies. And this raises the fact that in particle physics in particular, and in quantum field theory, there are a set of scales characterized by nature, or maybe the other way around. Nature is characterized by a set of scales. So I want to talk about that a little bit today, but of course, because this is what we do here, I want to dig in a little bit more to where some of these scales come from and how they relate to each other. It turns out that the whole idea of where scales come from is enormous and difficult, and we're not going to get to all of the different scales, and some of them we don't know, some of them we do know, but we'll have to wait a little bit to figure out where they come from. So when I talk about the size of things, what is that supposed to mean? Well, it depends on what units you're thinking about, right? Size could mean length, of course. It could just mean distance, but it could also mean any combination of lengths. So area is length squared, volume, of course. But then, of course, you also have time, right? Space-time, we know, is one thing. So if you can measure lengths, you can measure time. And then we have mass, we have energy, we have a whole bunch of different ways in which you could talk about the size of different things, the size of the energy scale, the size of the mass scale. So we are highly trained particle physicists, so we will use natural units, and that will make our lives much easier. I'm not sure why it was the particle physicist who got to come up with the name natural units. There's a whole bunch of unit systems out there we can use. So we set h bar, Planck's constant, the reduced Planck's constant with the 2 pi in it, equals 1, and the speed of light, c, also equals 1. And then we need to pick a unit, right? We need to pick one unit to actually stick with. So we know, what we went over before, is that the units of energy in natural units are the same as the units of mass. And that's because you know that there's an equation, E equals mc squared, and if the speed of light is equal to 1, then energy just equals mass. You could equally well, to make that argument, use the equation for kinetic energy, right? E equals mc squared is the rest energy. The kinetic energy in non-relativistic physics is E equals 1/2 mv squared, and the half is dimensionless, m still has the dimensions of mass, and if the speed of light is equal to 1, that means every velocity is dimensionless, because every velocity is measured in the fractions of the speed of light. So E equals 1/2 mv squared also tells you that in natural units, energy and mass have the same units. And we're going to measure them using electron volts, EV, okay? I will explain a little bit. I gave the technical definition of electron volt. If you have a volt of electrical potential, it requires 1 electron volt of oomph, of energy, to move it across that 1 volt of potential, let's say between the ends of a 1 volt battery, I guess. That's completely meaningless. Who does that in their everyday life, moving electrons across 1 volt batteries? But we'll give you a feeling for how much an electron volt is during this video by sort of comparing it to other things that we actually have feelings for. Sometimes we use GeV, G for giga. This is billion electron volts, okay? So 10 to the 9 electron volts. In fact, particle physicists are shameless about using electron volts, but also GeV for billion electron volts, but also MeV with a capital M for mega electron volts, 10 to the 6, KeV, kilo electron volts, 10 to the 3, MeV with a lowercase m means millielectron volts, 10 to the minus 3, TeV, tera electron volts, etc. I'm going to try to mostly use electron volts. Sometimes I will use GeV because I'm so used to using GeV for certain things that that's what I just understand the units in, the different quantities. But I'm going to try to, like, if you don't know it, I'm going to try to make your life easier by just sticking with EV most of the time. And then you have, space and time, so length and time have units of 1 over energy. So we will measure those in units of 1 over electron volts. So if you want to know how tall somebody is, you can give their height in inverse electron volts. Okay, that's one of the lessons of this lecture. And the conversions in natural units, just to relate to more natural things, 1 gram. Interestingly, there's not a unit of energy that everyone is familiar with. Like probably the unit of energy most people are familiar with is the kilowatt hour. How many kilowatts you use in an hour. Sorry, it's the other way around. Kilowatts times the number of hours. So kilowatt is a rate at which you're using energy. So if you go to your electrical meter outside, it measures the rate at which you're using energy, and then it integrates it over time to get kilowatts times hours, and that's a unit of total energy. But also, completely bizarre unit of energy. In CGS units, centimeters, grams, seconds, energy is measured in ergs. In MKS, meters, kilograms, seconds, it's measured in joules, but very few people have a feeling for either what an erg or a joule actually is. So I'm not going to tell you how to convert, but there it is, electron volts. You can just look it up. I will tell you how to convert grams. 1 gram is approximately 10 to the 33 electron volts. And just to reiterate that I'm very much a theoretical physicist here, we are going to use one significant figure in all of our calculations. So of course, there's a much more precise number relating grams to electron volts, but since we only really care about the basic way that things relate to each other, we're not going to be plugging in and building any machines based on this. I'm just going to give you the order of magnitude here, okay? So 1 gram, 10 to the 33 electron volts. So as a mass, 1 electron volt is really, really tiny, okay? 1 electron volt is 10 to the minus 33 grams, and grams are pretty tiny. A gram is the mass of 1 cubic centimeter of water. And a cubic centimeter is about 1/5 of a teaspoon for you Americans out there. So a gram is a very tiny amount of mass. Electron volts are much tinier than that. 1 centimeter is approximately, what do I have here? You can write it 2 different ways. 10 to the 5 inverse electron volts, right? Because I said that the units of length in natural units are inverse electron volts. But sometimes it's more convenient to write this as the quantity 10 to the minus 5 electron volts to the minus 1 power, okay? So if you're using units of inverse EV, 1 centimeter is 10 to the 5 of them, 100,000 of them. But what you want is some sort of physical relationship, right? If someone is quoting you a length in electron volts, you want to know, like, okay, what is the length that 1 electron volt corresponds to? Or vice versa, what are the number of electron volts that 1 centimeter corresponds to? So 1 centimeter corresponds to 10 to the minus 5 electron volts to the inverse power. As we'll see when we dig in a little bit, you'll get a little bit more of a physical feeling for what that actually means. And 1 second, traditional unit of time, is about 10 to the 15 inverse electron volts. So in other words, 10 to the minus 15 electron volts to the minus 1 power. So time and space are related to each other by c equals 1. It should not be a surprise to you that 1 centimeter corresponds to a much smaller number of inverse electron volts than 1 second, because in 1 second, the speed of light says that light is going to move a lot more than 1 centimeter, right? It's going to move a very big distance. So 1 second in energy units corresponds to a much, much, much tinier energy than 1 centimeter does. Okay, so that now with those in hand, we can do the traditional thing. This has been done many times, the powers of 10 kind of diagram. And I don't want to belabor it too much, but I know that some people have been asking in the videos, like the Planck Scale, what is that? Or, what is an electron compared to a proton, things like that. So we can actually just go over these very, very quickly. If I can get them right, I think we'll be in good shape here. So I think I can draw this way. Let's see. Okay, that's close enough to a straight line. And I'm going to not cheat a little bit, but I'm going to ask your indulgence a little bit. What I want to talk about 30 orders of magnitude of difference between energies. At the low end, I'm going to say that this is 10 to the minus 3 electron volts. And I want to go all the way up to 10 to the 27 electron volts. Okay, so that's why I've divided it into 3, because then by powers of 10, this is 10 to the 7 electron volts, and this is 10 to the 17 electron volts. Okay, sadly 10 is an awkward number. We only pick it because we have 10 fingers. So what I'm going to do is draw 1, 2 little subdivisions, and they're going to go by 3 and then by 4, right? Does this make sense? So this is, I'm going to have to write smaller, I suppose, 10 to the, well, this is just 1 electron volt. This is 10 to the 3 electron volts. Then, so that's 3 between there and there, another 3 between there and 3 between there and there, 3 between there and there, 4 between there and there. That's what I'm trying to say here. And then same thing here. So this is 10 to the 10 eV, 10 to the 13 eV. Same thing here. This is 10 to the 20 eV, 10 to the 23 eV. Okay, this is just the way that I thought that would be most convenient to actually do this. And then I'm going to tell you where the different masses of particle physics are. So for example, an electron has a mass of about 500,000 electron volts. So I'm tempted to just call that a million electron volts, but that factor of 2 kind of really does matter. So it's a little bit less than a million electron volts. So let's put it here. This is the mass of the electron. So what I'm going to do here to start is convert masses into energies and just tell you where the mass scales are. And then we'll talk about some real energies later. So this is 5 times 10 to the 5 electron volts. So a capital MeV is a million electron volts, mega electron volts. You will often see the electron mass written as 0.5 MeV, okay? Whereas protons and neutrons are about 1 GeV, about 1 billion electron volts. So that's here. Let me write it like there. Okay, so this is protons, neutrons, and that's 10 to the 9 electron volts, 1 GeV, 1 giga electron volt. And then things like the Higgs boson, which is 125 GeV, the top quark is 174. So again, ignoring anything other than the order of magnitude, that is 10 to the 2 times the GeV, so that's 10 to the 11 electron volts. Okay, so that's here. This is Higgs. Top quark is about the same, 10 to the 11 electron volts. Okay. And then everything that we know in the standard model of particle physics is mostly in between, right? Things like muons and taus are in between electron and Higgs. All the quarks are in between here. So this is basically the range. That's it. And you might ask, well, why do we have to go all the way from 10 to the minus 3 to 10 to the 27? 10 to the 27 electron volts is, of course, the Planck scale. This is what we call the reduced Planck scale. There's a factor of 4 pi or something like that that goes in there, but 10 to the 18 GeV or 10 to the 27 electron volts is about what we mean. So you can see the huge range. You know, it covers a lot of sins, the fact that we put 30 orders of magnitude into this picture. This is an enormous difference between the mass of the Higgs and something like the Planck scale, okay? It's a really big difference. But there it is, and it's important once gravity comes into the game, and you can instantly see sort of why gravity is not important in particle physics. The Planck scale, the Planck energy, is basically the energy at which you would have to do some particle collisions before gravity became noticeable compared to the other forces of nature. And here we are doing experiments at, let's say, the Large Hadron Collider. It is roughly here, you know, 10 or 100 orders of magnitude, 10 or 100 times bigger. What is the LHC? Roughly speaking, at this order of magnitude level, 10 TeV, so 10,000 GeV. So that is 10 TeV is 10 to the 12, 10 to the 13. Yeah, there we go, 10 to the 13 eV. So let's say this is where we'll put the LHC. I really should sort of rehearse and plan these lectures a little bit better. Okay. And then, of course, you have things like atomic nuclei, right? Like an atomic nucleus is typically a collection of protons and neutrons. It's always a collection of protons and neutrons. So nuclei sort of span some range here. So it's all the physics that we know is in this little range, except there is, of course, the neutrino, right? Neutrinos, there's three of them, electron, neutrino, muon neutrino, tau neutrino. Neutrinos are remarkably complicated and subtle, actually, even though I say there's three of them. There's also three different masses for neutrinos, the lightest one, the middle one, and the heaviest one. But there's something called neutrino mixing, which says that the lightest neutrino is not the electron neutrino. It's a combination of the electron, the muon, and the tau neutrino, and likewise for the middle one, and likewise for the heaviest one. There's not a one-to-one lineup between what we call the flavors of the neutrino. Are they electron? Are they muon? Are they tau? What that means is, are they produced along with those particles? So when the muon decays, it can turn into an electron, but only at the cost of making a muon neutrino, so the muonness is conserved, and then an electron antineutrino, so electronness is not created. And those flavor states of neutrinos do not line up with the mass states, and this is why neutrinos are complicated. But we don't even know what the masses are. We think that they are somewhere in between 10 to the minus 3 and 1 electron volts. That's why I need to go down all the way here. And also, interestingly, there's another parameter that is down there, which is, remember we talked about the cosmological constant, the vacuum energy that pushes apart the universe? So we said that there's an energy density, rho lambda, equals the energy density in empty space. The amount of energy in any 1 cubic centimeter, or something like that. And so that has units of energy to the 4th power. So we can write it as some energy scale, evac, to the 4th power. And you run through the numbers, you compare to the observations that we've made, and evac turns out to be about 10 to the minus 3 electron volts. So that's not the mass of any particle, okay? That's not the mass of anything. That is the scale. That is the energy scale that you raise to the 4th power to get this number, the energy density of the vacuum. But that's okay. This wonderful thing about natural units is we can compare energies and other scales and masses all to each other at the same time. Now, you might say, it's interesting that the energy density of the vacuum is at the same energy scale as the mass of the neutrinos. Does that have anything to do with anything else? No one knows, because no one knows what the explanation for the vacuum energy actually is. But you would not be the first to try to relate them if you went out and made a theory that had them related to each other. Okay, what else can we talk about? Well, we don't know what the dark matter is, okay? We're not sure what the dark matter is, but there are ranges of possibilities for the dark matter. So one particle that could be the dark matter is the axion. Axions could be maybe 10 to the minus 4 electron volts. Very, very light particles. Some of you, we haven't gotten into cosmology in detail yet, but some of you might know that one of the things we know about the dark matter is that it's cold. It moves slowly. And you might say, well, I would think that light particles should be moving fast because they're light. So even a little bit of energy would make them move very rapidly. Why are axions qualifying as cold dark matter? The answer is that they're made with zero momentum from the start. When the axions are born, they're born at rest. And this is a complicated story about axions, which makes them very interesting to cosmologists. The other possibility is that the dark matter's up here, sort of LHC type scales, okay? So if you have weakly interacting massive particles, WIMPs, I should put question marks here because we don't know if these particles exist, but WIMPs could be at the scale where the Large Hadron Collider is looking. Maybe a little bit less than that, actually, to be honest, because the hope is that you have more than enough energy to make them. So let me be a little bit more honest there and put the WIMPs up here. Okay, they might be comparable to the Higgs, a little bit less than the Higgs. We don't know. They could be as much as a proton or something like that. And then there's this idea called grand unification. There's this idea that we don't know if it's true. It became very popular in the 1970s because there's 4 forces of nature that we can easily recognize: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. In some sense, you can qualify electro and magnetism as 2 different forces, but Maxwell unified those back in the 1800s, so we call them one force. In the 1960s, Steven Weinberg played this trick where he showed how to unify the electromagnetic force with the weak nuclear force to create what we now call the electroweak theory, and the energy scale of the electroweak theory is about these energies we've been talking about, like somewhere around the Higgs boson, the LHC, etc. Okay, 100 GeV or 10 to the 11 electron volts. That's a typical scale for the electroweak force. Now, gravity's always been hard. Gravity is a hard thing to put into the quantum mechanical framework, but the strong force is perfectly quantum field theoretic, so an obvious next thing to do is to do what Weinberg did, but do it again. Rather than just unifying electromagnetism and the weak force, unify it with the strong force as well. And that attempt was called grand unification. So grand unification doesn't even include gravity. It's just supposed to be the electromagnetic weak and strong forces. And what you can do is predict using physics, etc., that there's a typical energy scale, the Grand Unified Theory energy scale. Again, question mark time, because we don't even know if it's true, but it's something 2 orders of magnitude, maybe 3 orders of magnitude below the Planck scale, 10 to the 23, 24, 25 electron volts. Again, we don't know, so there's some wriggle room there. So this would be the scale at which all of the different forces differentiated, or at least the strong force differentiated from the electroweak force, then electricity and magnetism differentiate from the weak force down here near where the Higgs boson is. So this is something that, again, is hard to probe experimentally. It's very hard to build a particle accelerator that reaches those energies. The hope of grand unification was that because it unified everything, it gave you a way for protons and neutrons to decay into particles that were not strongly interacting at all. Now, neutrons decay all the time, but they decay into protons. Protons, according to every experiment we've ever done, don't decay at all. But according to grand unified theories, they should decay, so people started building proton decay experiments, and they were very disappointed that the proton is not observed to decay. This is since the 80s, we've been looking for this and haven't found it. This is the first hint that our attempts to go beyond the electroweak theory haven't been paying off yet, and that's still true, 40 years later. So what you get is, in between here and here in these theories, you get what is called a desert. Sometimes called Glashow's desert, after Sheldon Glashow, who was one of the people, along with Howard Georgi, who was the originator of the grand unification idea. The idea that maybe down here near 10 to the 10 eV, 10 to the 12 eV, there's a whole bunch of particles, and there's nothing new going on until you reached grand unification. Maybe that is true. Maybe it is not. We don't know. We haven't looked yet. But there is this big gap in scales. That is one thing that I absolutely want to emphasize to you. So there's another thing. Okay, so this is the powers of 10 story at the particle physics level, okay? It would be nice to relate these to some more tangible things. Most of us have never seen a proton with our naked eye. Most of us have never seen the Planck scale with our naked eye or anything like that. How do you relate these? Like, is this a lot of energy or a little bit of energy? Okay, so let me give you 2 different scales you can compare to. Let's make another color here. What if you clap your hands like that? I mean, not like that, because that's very slow. What if you clap your hands as fast as you can, right? Do your best to move your hands as fast as you can. I don't know if I got this right, but this is the homework I did for you folks. I sat down and I calculated the kinetic energy involved in clapping your hands together. Don't trust me on this. I'm not very good at those kinds of back-of-the-envelope calculations. But the answer I got was that a clap is around here. This is the kinetic energy you get by clapping your hands together, the energy released in sound and heat when you clap your hands together. It's about 10 to the 18 electron volts, okay? And if you have a sort of medium-sized jet airliner or a very big freight train loaded, and they're moving at, 100 miles an hour or whatever they move at, those will have an energy that is basically the Planck scale. Either I think a Boeing 767 was what I read. Trains, of course, depends on how much you load them, how fast they go, etc. But the kinetic energy that you pack into a moving train or plane is about the Planck scale. So on the one hand, the Planck scale is a lot of energy. Like, you don't want to get hit by a moving freight train, okay? But on the other hand, you can clap your hands together and you create more energy than any particle accelerated by the Large Hadron Collider. So you might be wondering, like, why did we spend $9 billion to accelerate particles to these energies when I can create much more energy just by clapping my hands? The answer, of course, is that the amazing thing about the LHC is not that the energies are high, but that they are packed into a single particle. Likewise for the Planck scale up here, the amazing thing is not that the energy is just enormously big, but that it is perhaps packed into a single particle, or at least packed into a single energetic event. Whatever is happening at the Planck scale, the first excited modes of superstrings would have energies near the Planck scale, and that would have, in a single particle, the energy of a moving freight train. Okay, so that's why it is so much energy. It's a lot of energy in one little tiny package. That's why it's hard to make. I mean, you can smash airplanes together all you want. The total energy might be of the order of the Planck scale, but you're not concentrating them into one particle. All the individual protons or neutrons that are hitting each other will have energies way, way below the Planck scale, so no interesting quantum gravitational effects are going to take place. Okay? Another way of comparing these energy scales in particle physics to everyday scales is to compare masses to energy, right? So as far as masses are concerned, let me get this out of the way because you already saw that and I need the space. So to compare masses to energies, remember that as far as mass is concerned, one proton is about the same as one neutron, and that's about 1 GeV, which is 10 to the 9 electron volts. For comparison purposes, an electron is about 1/1800th of a proton in terms of mass. Okay, so when you make up ordinary matter, almost all the mass comes from comes from protons and neutrons, comes from the nuclei. Electrons are important for the chemical and electrical properties of the matter, but as far as the mass is concerned, forget about the electrons. All the action is in the protons and neutrons. And conveniently, protons and neutrons are about the same mass. If you're a little bit more careful here, I'm going to get the numbers wrong, but I think that the proton is 0.938 of a GeV, and the neutron is 0.939 of a GeV. It's just a little tiny bit more than that, but to our precision, we're going to talk about it as just one GeV. And then, let me get this right. Okay, a gram is 10 to the 33 electron volts. So 1 gram of mass, 10 to the 33 electron volts. So that's 10 to the, 33 minus 9, 24 proton masses. So 10 to the 33 electron volts doesn't even fit on our plot, right? 1 gram, 1/5 of a teaspoon of water has more energy in it, by which we mean if you literally converted all of that rest energy, all of the energy, like if you did nuclear explosion, better than a nuclear explosion, if you had half of a gram of matter and half of a gram of antimatter and combined them together and they completely annihilated, the energy released would be 10 to the 33 electron volts. So that little tiny bit of mass by everyday scales has an enormous amount of energy by particle physics scales. That's the point I was trying to get to. And this number, 10 to the 33 electron volts, might actually secretly be familiar to you because I've been hiding it by not doing the precision. But there's something called Avogadros number. Avogadros number is useful in chemistry just by fixing a certain amount of stuff, but it's also useful as a rough guide for when things become macroscopic and everyday. In typical things that about 1 centimeter across, you might get, roughly speaking, Avogadros number of particles, okay, or of atoms in them. And Avogadros number is, let me get it to one significant figure, 6 times 10 to the 23. 6 times 10 to the 23, when you round up, is 10 to the 24. That's what Avogadros number is. It's roughly speaking the number of hydrogen atoms in 1 gram of hydrogen. Or if you have something like carbon, which is actually used as the mass standard here, Avogadros number is the number of carbon atoms in 12 grams of carbon, because the atomic weight of carbon is 12, okay? Chemists, bless their hearts, care about the real world where there are isotopes, and so they care about the fact that, hydrogen is not all atoms that have one proton and one electron. Sometimes there's deuterium with a proton and a neutron, or even tritium with a proton and two neutrons. We physicists can ignore that and imagine the spherical cow where all hydrogen atoms are one proton and one electron. But Avogadros number is, roughly speaking, the number of atoms or the number of particles in a gram or a few grams worth of stuff. Okay, so Avogadros number is the connection between microscopic numbers, protons and neutrons and their masses, and macroscopic numbers, grams and cubic centimeters and things like that. Now what we could do is redo this powers of 10 plot. By the way, I should, just for consistency's sake, mention that this is a logarithmic plot. That is to say, the distance between the different tick marks is not a fixed amount of energy, it's a fixed scaling in energy, right? Every tick mark, the energy goes up by 10 to the 3 as a multiplicative power, and we'll get back to that a little bit later, maybe, depending on how long this video goes. So you can do this again, and you can do this sort of powers of 10 thing for sizes, for distances, or for times in cosmology and stuff like that. I'm not going to do that because you can get that on the internet. You can go to Wikipedia and get that stuff. But I should just give you some numbers for comparison. So I wrote some numbers down. How many, and so from now on, so since we know that a proton is about a GeV, 10 to the 9 eV, let's, once we get to the macroscopic scale, use that as our unit of measure. How big is something means how many proton or neutron masses are in it, which is the number of protons and neutrons, roughly speaking. So a bacterium, it turns out, has about the same number of protons and neutrons as a single human DNA strand. I think this is true. I mean, I don't know. I looked it up on Wikipedia. So a bacterium, or a human DNA strand. Bacteria have their own DNA, of course, but it's shorter than a human. Is about 10 to the 12 protons. Nowhere near Avogadros number, which is just a reflection of the fact that a bacterium or a DNA is much smaller than a gram. That's not surprising. A person has about 10 to the 28 protons. Most of us are more than 1 gram, sadly. The Earth, not really sadly, that was a joke. The Earth is about 10 to the 51 protons. Again, this is not the number of protons in the Earth. This is the mass of the Earth in units of 1 proton mass, okay? Most of the Earth is neutrons, not protons. The Sun, 10 to the 57, if I can read my handwriting here. The Milky Way galaxy, about 10 to the 76, it looks like. I'm not sure if that's 76 or 70. You can look it up. That's your homework. How heavy is the Milky Way? And the observable universe is about 10 to the 82. Again, don't trust me on any of these numbers because you know why? I don't care. It doesn't really matter what these exact numbers are. Of course, it matters a lot if you're a biologist or a chemist or an astrophysicist or whatever. All I'm trying to do is emphasize the fact that, once again, the scaling differences are enormous. There's an enormous hierarchy between the size of the universe, the size of a galaxy, the size of the solar system, the size of a person, the size of a bacterium, the size of a proton. That's interesting. That's interesting all by itself, right? Why are these hierarchies there? Part of the whole philosophy of scaling is if you have a certain mass scale out of which everything else is created, if you didn't know anything else, if you said, okay, the world is made of protons and neutrons and they have about the same mass, you might expect, with good reason, that 1 or 2 or 10 proton masses would be a typical scale of stuff in the universe, right? Because that's what everything else is built out of. Now, it's not true, that everything else is simply built out of protons and neutrons. This is part of the explanation. Electrons are important, gravity is important, and so forth. But the point is that, therefore, you demand an explanation. You want to know, like, why isn't everything, roughly speaking, one proton mass? Where do these enormous differences in sizes come from? I'm not going to get to explain that all, but we'll give it some hints of where these numbers come from along the way. So this is the appropriate time to get back into that question of what is the physical meaning of the conversion between energy and mass and length and time, okay? What does it mean when you say that a certain distance is a certain number of inverse electron volts? And the answer comes in the form of this idea called the Compton wavelength of a particle. The Compton wavelength came out of an analysis of electromagnetic scattering by Arthur C. Compton. Compton, anyway, whatever his initials were. But it actually can be explained best if we admit that individual particles are not individual particles, but come out of quantum fields, okay? So the Compton wavelength has a very simple definition. We're going to use the letter lambda for it. I try to minimize my use of Greek letters, but lambda is just what we use for wavelength. Sorry about that. It's the Greek version of L, if you want. That's why length is appropriate. And the definition of the Compton wavelength of a particle, if I put all the constants back in, is h bar over the mass of the particle times the speed of light. We set h bar and c equal to 1, so it's just 1 over the mass of the particle. Okay. So that's kind of not very helpful. You just said, okay, I take the mass and I invert it and I get the wavelength. So because distance or wavelength has units of 1 over energy and mass has units of energy, this makes perfect sense units-wise, okay? I mean, basically the Compton wavelength is the mass, except we're expressing it in different units. Now, why? Why do we care about this particular number? First, let me tell you what the number is. So the number for an electron, the Compton wavelength, is about, I'm going to give you one significant figure, so thank me for this, 2 times 10 to the minus 10 centimeters, whereas for a proton, Compton wavelength is about 1 times 10 to the minus 13 centimeters. Now that makes sense. Remember I told you an electron and proton are different in mass by a factor of about 1800. So if I go to one significant figure, a factor of 2000, and here you go. There's the 2000. But what I want to emphasize is the Compton wavelength of a proton is shorter than the Compton wavelength of an electron. I mean, that's obvious because it goes as 1 over the mass. But in ordinary ways of thinking, in ordinary world language, you think of heavier things as being bigger, okay? You have more stuff in a heavy thing. In order to put more mass in something, given the same construction materials, it will generally take more size. So we have this intuitive feeling that heavier means not just more massive, but larger in physical dimension. But that's because we're imagining that something is made out of some pre-existing materials, atoms arranged in certain configurations. This is different. The Compton wavelength, I want to argue, is what you should think of when you think of the size of an elementary particle. And in quantum mechanics, heavier particles are smaller in some very real sense. So let me actually explain the sense in which the Compton wavelength should be thought of as a size. So remember you have the uncertainty principle. Okay? So you're relating the error were you to measure the location of a particle, delta x, times delta p, the uncertainty were you to measure the position of the particle. And we said that it's greater than h bar over 2, but in my 1 order of magnitude precision, 1/2 equals 1, okay, 2 equals 1. Only particle physics could get away with that. So you have to be careful. When you set 2 equal to 1, you better be careful that it's really only 2 that is you're setting equal to 1, not 2 to the power 100. That would get you in trouble, because 2 to the power 100 is very different than 1 to the power 100. But if there's just a single factor of a half rolling around, then we ignore it. And of course, h bar equals 1, so delta x, delta p is greater than 1. That's the Heisenberg uncertainty principle. And we also have the relativistic energy formula relating energy to momentum. We have the energy squared equals the momentum squared. This is a vector, but I'm going to ignore the vector signs, plus the mass squared. So when the momentum is 0, E squared equals M squared, or E equals M, because C equals 1. And I've ignored all the other factors of C, etc. There's factors of C floating all around here if you try to convert from momentum to velocity, for example. Okay. So consider a particle with 0 momentum. let p equal 0. But imagine that you have delta p, the uncertainty in the momentum, of order the mass, okay? So what I'm saying here is, imagine you have a particle and it has a wave function. So we're not just thinking classical particles. We're thinking of a particle with a quantum wave function. And the wave function might look like a wave packet. So here's psi as a function of x, and it's sort of flat, and then it wiggles, and it's flat again, okay? So you have a certain delta x, the size over which the wave packet wiggles before it goes to 0, to the left, or to the right. And if you decomposed this wave packet into modes with different wavelengths, you'd be able to figure out that there's an uncertainty in momentum as well. So I'm asking you to imagine that we have a particle sort of in a more or less confined region of space that we know its momentum on average is 0, but there's some uncertainty. So there's some contributions from 0 momentum, some contributions from small momentum, some contributions from large momentum, etc. We're not exactly sure what answer we would get were we to measure the size of this particle, the momentum of this particle. And let's imagine that that momentum, that uncertainty, delta p, is of the same order as the mass of the particle. Okay, we can do that. One way of saying it is, if you were to measure the energy, right, you need to take into account the fact that the momentum is unknown. So the energy that you might get, were you to measure it, is likely to be greater than 2 times m squared, because you have m squared itself, and then you have the contribution from the fact that you don't know what momentum the particle has. But what that means is, once the change in energy, the uncertainty in momentum becomes that large, the uncertainty in energy becomes that large, that you don't even know if you only have one particle there, right? Once you get up to 4m squared, you have enough energy to make an extra particle. If you know that what you're doing is really quantum field theory and not quantum mechanics, then you know that your quantum field is a superposition of there are no particles there, there's one particle there are 2 particles there, and so forth. And here what you're saying is you're probing the particle in such a way that you're not even sure that what you will see is a single particle anymore. So the way to get around this is to say the one particle regime, the part of the wave function of the quantum field that really describes really just one particle, has the feature that delta p is less than m. Yes, that's correct. And therefore, you look over at the uncertainty principle, so delta x times delta p needs to be greater than 1, but delta p is less than m, so therefore, my deltas are deteriorating, sorry. Delta x has to be greater than 1 over m. Otherwise, you're not going to satisfy the uncertainty principle. So, in other words, for the wave packet to have the shape and size that lets you have enough certainty about momentum that you know you're not making new particles, the linear extent of the wave packet has to be large enough that it's larger than 1 over m, which is, of course, the Compton wavelength. That's what the Compton wavelength is. I'm not sure that was the most elegant explanation of it ever given. The Compton wavelength is not necessarily the wavelength of the actual wave function of a particle. It's the smallest the wave function can be so that we can actually know with high confidence that there really is only just one particle there. It's the smallest box we can squeeze a particle into and still stay within this one particle regime in quantum field theory. If you try to squeeze the particle smaller than that, or if you try to measure its position with a precision higher than that, then you're not sure you're talking about just one particle. That's what the Compton wavelength is. There it is. The Compton wavelength, 1 over the mass, is basically how small the particle's wave function can be, so we're sure it really is just one particle. So, in other words, if you try to make something out of particles, you can't make things out of individual particles with sizes smaller than their Compton wavelength. So particles, individual particles that you would know and trust are really one particle at a time, can't be smaller than the Compton wavelength. I'll put a C under there just to make sure that you know it's the Compton wavelength. But if I'm talking about individual particles, I will sometimes put the subscript with the name of the particle, okay? So that's what the Compton wavelength is. It's sort of the minimum size that you can squeeze the wave function and you still call it a particle. So the bad news is, therefore, Ant-Man is not real. You know, in the movies, not just Ant-Man, but Fantastic Voyage, many, many movies that you've seen in different contexts, there's the idea that you can take a macroscopic thing, like a person, and just shrink it, right? Just make it smaller. Now, usually, those thought experiments do not tell you whether that happens because the thing that you're making out of has fewer and fewer atoms, or because the individual atoms are smaller. Okay, they're a little bit silent about that. But Ant-Man goes down all the way to the size of an atom. And therefore, he's not just a single atom. So that's not possible unless the individual atoms became smaller. And if that were true, they would have to become heavier. If you're making the Compton wavelengths of these atoms tinier, by the laws of physics, they would have to get more and more massive. So Ant-Man would actually be enormously massive to have that many atoms in his body squeezed down to that tiny little size. But that's not what he is. He's actually very light. So that's not realistic according to the laws of physics. Another way of spinning the same conclusion is, you might wonder, you know, there's human beings who live on planets that circle the solar system, the sun, and then the sun is part of the galaxy, and maybe the universe is part of something bigger. We seem to be in this nest of hierarchy of many different things, and if you go small, we're made of cells that are made of molecules that are made of atoms, and you might casually ask yourself, I wonder if it just keeps going. I wonder if electrons are made of tinier things and quarks are made of tinier things. I wonder if there could be like a whole civilization that rises and falls on the surface of an electron, just like it does on the surface of the Earth going around the sun. No, it can't. That's what this means. That's what the Compton wavelength tells you. If you want to stay in a regime where you're made of particles, where you're not just high-energy wave functions, then there's a minimum size that your particle can have, given that it has a certain mass. So this is why we know that electrons and other things are simple. We have other ways of knowing also, but there's no hidden amounts of variability in electrons or anything like that. If there were little wiggles in the wave function of the electron or extra wave functions that also had really, really tiny wavelengths, they would need to have high energies and they would be more massive than the electron. So you can't do it. You got to keep your electrons simple. So size for elementary particles is proportional to 1 over the mass. That's a crucial lesson that we got here. Okay, that's good. For elementary particles, crucially important here, because we know this is not true for pickup trucks or anything like that, right? More massive things tend to be larger in the macroscopic world. So how do we relate those two things? You know, where does the big size of macroscopic things come from if the size of individual particles comes from the Compton wavelength? Remember, again, particles can't be smaller than the Compton wavelength, but let's emphasize, particles, and by which we mean the wave function of a certain kind of particle, can be larger than the Compton wavelength. So the Compton wavelength is a minimum size for particleness to be a sensible concept, but they can be larger, and in fact they are. So let's see, for example, hydrogen. You know, we talked about hydrogen atoms. Hydrogen atoms just a single proton, an electron going around it. If someone told you that, if someone says, okay, here's physics, here's a proton, here's an electron, they're bound together by electromagnetism, how big should the hydrogen atom be? Well, you have the Compton wavelength of the electron, which we said 2 times 10 to the minus 10 centimeters. We have the Compton wavelength of the proton, 10 to the minus 13 centimeters. Okay, proton much smaller than the electron. So you might say, well, the hydrogen atom should be roughly the size of the electron, so it should be 2 times 10 to the minus 10 centimeters across. Now, by dimensional analysis, I should note that we can construct the number lambda p divided by lambda e, the Compton wavelength of the proton divided by the Compton wavelength of the electron. This is about 10 to the minus 3. Okay, forgetting the factor of 2 right now. So this is a dimensionless number, and we could raise it to any power. If we raise it to the power 10, then this is 10 to the minus 30. So scaling arguments only take us so far. When you have two masses in the game, or two Compton wavelengths, two lengths, I'm going to erase this because it's a silly thing. But you can create whatever number you want in principle. So you have to think a little bit, in other words, okay? So let's do some thinking here. If the Compton wavelength of the proton is tiny compared to the Compton wavelength of the electron, even if you don't say, if you don't leap to the conclusion that the hydrogen atom should be the Compton wavelength of the electron, there's no reason for the Compton wavelength of the proton to have anything to do with anything. It's just a very tiny little number. We would naturally expect, even if we didn't work through and solve the Schrodinger equation, that the proton was confined to a more or less tiny little spot and the electron was spread out over the atom, which is exactly true. So in some sense, the thing that sets the scale for the size of the hydrogen atom is the Compton wavelength of the electron, not the proton. And that's true. But the question is, are there other things, other considerations that come into the game? Well, there is. There is electromagnetism, okay? Electromagnetism is what binds the electron to the proton. And electromagnetism has a strength. You can think of the potential, V of R, okay, the electrostatic potential, as a function of the distance between two objects. One way of writing it, and this is, we're going to gloss over some constants of nature and things like that, is as minus alpha over R, where alpha is the fine structure constant, 1 over 137, roughly, okay? So alpha is the number that tells you the strength of electromagnetism. It tells you how important the electromagnetic force is when it comes to binding two things together. And 137, roughly 100, okay, so this is, in our very sloppy way of thinking, 10 to the minus 2. So there's a factor of 10 to the minus 2 that might come into the game when we figure out what the size of something is, right? That's a dimensionless number. Alpha doesn't have any units at all. We could multiply it, or we could divide it. What are we supposed to do? Well, so we can actually draw this potential. Very, again, we're being a little bit impressionistic here. So here's R, here's V of R, and R is the distance from one object to another. So by construction, it is a positive number, or 0. It can't be a negative number. But I'm going to draw it as if it's negative because I don't want to draw a three-dimensional thing. And the potential looks like this, 1 over R, right? Again, I made 1 over plus R down here, so the potential is always a negative number. And the electron wants to be near 0, but because of the uncertainty principle, it will not be exactly at 0. And what can we say about the wave function of the electron in the hydrogen atom? So it's going to look something like this, right? It's going to be some spread out thing. If it were squeezed in more, that would cost energy from the change over space. If it were squeezed out less, if it were broader, then it would be further away from the proton where it doesn't want to be. So there is some give and take. And what we can say is, we can just sort of figure out how things should scale. As alpha goes to 0, so alpha never does go to 0, what we mean is, if we were to imagine a fake world in which the fine structure constant were very, 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 very tiny, how would that be different from the real world? Well, what it would mean is the electron would be bound less strongly. There would be less of an attraction between the electron and the proton to make a hydrogen atom. And therefore, what we would guess is that, how do I write this? The size of the atom would go to infinity, right? The electron wants to be spread out. If there's an electron in empty space, if there's an electron that is not bound to a proton, its wave function just spreads out as much as it can. That is the prediction of the Schrodinger equation. So as the binding to the proton is artificially turned off, that electron would puff up and become bigger. So that means that the size of the hydrogen atom is inversely dependent on the fine structure constant. So you might guess, well, let's not guess. Let's just tell you the answer. There's something called the Bohr radius, named after Niels Bohr, who figured it out long before quantum field theory was known, or even quantum mechanics was known. They were inventing it at the time. The Bohr radius, which is traditionally called A0, which is a terrible thing to call it, but there's other things that are called R and B and so forth. So A0 turns out to be the Compton wavelength of the electron divided by alpha. Because as alpha goes to 0, the radius should get bigger, so divided by alpha. So that's 137 times the Compton wavelength, which works out to be about 10 to the minus 8th centimeters. So had you guessed that the size of a hydrogen atom, and the Bohr radius is roughly speaking the size of a hydrogen atom. More specifically, there's no such thing as a hard, fast wall at the end of a hydrogen atom, right? If you look at the yellow curve here, it tails off. It's supposed to tail off gently. It's not supposed to cross the axis. But the point is, there's always some chance, some probability you'll find the electron if you look for it anywhere. So the Bohr radius is the radius that says there's a 50-50 chance you'll find the electron within the radius or outside the radius. So it is one way to characterize the rough size of a hydrogen atom. You might have guessed, naively, that the hydrogen atom should be the Compton wavelength of the electron. It's proportional to that, but the constant of proportionality is a factor of 100, so it is bigger. And that's because electromagnetism is weak, because the fine structure constant is small. So in fact, this is sometimes called 1 angstrom unit, 10 to the minus 8 centimeters. An angstrom is just a very convenient unit to use in atomic or molecular physics, as it's the size of a hydrogen atom, roughly speaking, 10 to the minus 8 centimeters. And as it turns out, that's basically it. It's not just hydrogen that this is the size of. The Bohr radius is roughly the size of a hydrogen atom. It's also roughly the size of every other atom. The atoms do become bigger as you add more protons and neutrons. The nucleus becomes heavier. That's completely irrelevant to the size, because the nucleus is very tiny. The number of electrons, though, also goes up. That is relevant. We'll talk later about how electrons need to take up different shells and so forth. But still, you get factors of a few, or factors of 10 times bigger than the hydrogen atom. It's not linear with the number of extra electrons. So this is the number, 10 to the minus 8 centimeters, 1 angstrom, that sets the scale for atomic physics, for the length scale for atomic physics. And the next thing you want to do is put together more than one atom, right? Let's make a molecule. And that's going to be, like I'm not going to do all of molecules and chemistry and stuff like that, but we should be able to figure out, or at least say something about, the energies that are associated with molecules. So to do that, let's figure out something about the energy associated with individual atoms, right? So we drew this potential here for the electron. This is the potential energy of an electron surrounded by, in the vicinity of a single proton. And, remember we did the simple harmonic oscillator? Remember? Oops, yeah, remember? What do I want to do here? Come on, open up. Remember? Simple harmonic oscillator was a thing where we had a potential that was a parabola, x squared, and we said that the energy levels were equally spaced. There were energy levels En that were basically proportional to n. In fact, n plus a half, if you really want to be sticky about it. But they were equally spaced, so you could have an infinite number of energy levels in the harmonic oscillator. I'm not going to draw the wave functions again, but you remember I've drawn them before. And there's an infinite number of them. They go infinitely high. Same thing is true for the Coulomb potential, as we call it. Coulomb potential is the potential 1 over r minus alpha over r. So the potential itself looks like this. Oops, that wasn't very good. As a function of r. But the energy levels have a slightly different behavior. The energy levels, En, are proportional to minus 1 over n squared. I'm sorry that alpha is used for proportionality and for the fine structure constant once again. But basically, there is a lowest energy level, E1, and this works out to be 13.6 electron volts. So the difference between the energy of an electron that is outside the hydrogen atom, not in it at all, and the energy of an electron that is in its lowest energy state inside the hydrogen atom is 13.6 electron volts. But then that's E1, and then E2 is closer to outside, and then E3, E4, E5, and they pile up. There are also an infinite number of energy levels that an electron can have in a hydrogen atom. But as the number gets higher, as the number that we use to characterize which energy level we're in, they get closer and closer to zero difference between being in the atom and being outside. What that means physically is any little perturbation will just kick the electron right out. So an electron in its lowest energy level is stuck inside the hydrogen atom as much as it can be stuck. it takes this much energy, 13.6 electron volts, to kick it out and set it free. Whereas if an electron is up here in a higher energy level, it's easier to kick it out. It is bound more loosely. It is larger, its wave function is more spread out, and it's less tightly bound to the proton. What will happen if you just have an electron all by itself in a high energy level is generally it will give off a photon and go down to the lower energy level. So electrons tend to settle down to lower energy levels. Now this number, 13.6 eV, where did that come from? I mean, remember the mass of the electron is something like 5 times 10 to the 5 electron volts. So there's another big hierarchy here between the mass of the electron and the energy. The binding energy is 13.6 eV is the binding energy or the ionization energy of an electron in a hydrogen atom. Where did that come from? Well, we know that the energy of an electron, just the energy classically speaking, is the potential energy, and we know what that is. It's minus alpha over r, right? The energy V of r, the potential energy, is minus alpha over r. And we know that the typical r, the average value of r, is the Bohr radius, a naught. And a naught, where is it? Lambda over alpha. So the energy is, roughly speaking, alpha over r is lambda over alpha. This is alpha squared over lambda, or in other words, alpha squared times the mass of the electron. So there is this energy scale given to us by the mass of the electron, but science inserts a factor of alpha squared, which is 10 to the minus 4. In fact, it's a little bit smaller than 10 to the minus 4. So that takes us down from 5 times 10 to the 5 electron volts all the way down to just 13.6 electron volts. So it's 2 factors of the fine structure constant. That's where this particular hierarchy comes from. And this is why, again, this is a pretty good energy. This is as close as that one electron can get to the proton. As we will talk about later, in chemistry, in heavier elements, there will be some electrons that are stuck there close to the nucleus, and the nucleus is more charged in a heavier element like carbon or iron or whatever. So the most bound electrons are more tightly bound in carbon or iron than they are in hydrogen. But they're also irrelevant to chemistry, okay? Because they're just staying there. Chemistry is all the excitement because of the electrons in the outer shells of the atom, and they are less tightly bound than this one is. So basically, the energy scales of chemistry, all of chemistry, happens at energy scales of between 1 and 10 electron volts, roughly speaking. Okay, again, very, very roughly. And this is why. Because it's the mass of the electron times 2 factors of alpha times, again, some extra factors of n and n squared and things like that when you get to higher and higher energy levels. So this is how hierarchies get built, because there's one number, the fine structure constant, that is a little bit small, 10 to the minus 2, and it comes in multiple times. That's where atoms get their energy from. Well, what about molecules? Molecules. It's a very similar story. The only thing we have to play with are the masses of the nuclei, the protons and the neutrons, the masses of the electrons, and the fine structure constant. But they get hooked up together in more and more complicated ways. Happily, the answer works out very easily. I'm not going to actually try to justify this answer, but I'll tell you what it is so you can see, once again, this hierarchy at work. So you can have, in molecules, let's say that you have a very simple molecule. Let's say you have one atom that is just bound to another atom. Well, one thing is that these 2 atoms can vibrate, right? They can simply go back and forth. You will not be surprised to learn that for small vibrations, the energy of that kind of vibration looks like a simple harmonic oscillator, because everything looks like a simple harmonic oscillator when it is small vibrations. Small vibrations just look like harmonic oscillators. So there's a lowest energy, a next highest energy, etc. Vibrational energies are typically something like 10 to the minus 2 electron volts, okay? Things are a little bit farther apart. Larger distances means lower energies because distance goes inversely proportional to energy. There are also rotations. So let's imagine we have a more complicated molecule. Let's imagine a little molecule that has, three different. This is a heavy nucleus. Maybe this is methane or something like that, right? No, ammonia. Sorry. Well, this is a heavy nucleus and then three hydrogen atoms. And if we work in a frame of reference where we fix this one and don't move it, the one at the bottom, sorry, then let the other two move around, it's very much like when we said when you have a wave. Any arbitrary wave can be written as a superposition of plane waves with fixed wavelengths, sine waves and cosines, okay? That set of things you can add together to get any wave at all, we call the modes, okay? Here we have an interesting geometry, but the same kind of analysis applies. There's certain fundamental modes of oscillation from which you can build everything that actually happens. So if you think about, if you just fix your reference frame by fixing the bottommost atom and let the topmost atoms move around, what can they do? They can oscillate in and out, but they can also oscillate in and out either in phase or in opposite phase to each other, okay? That's sort of elongating or shrinking, I guess. They can move apart from each other, back and forth, or they can sort of wiggle in concert. And they can also have one go toward you and away, and vice versa, or they can go toward you and away in concert also. So there's a bunch of fundamental things that the molecule can do, and they have a fundamental kind of energy. So the rotation, the whole thing can rotate around also, or distortion of the molecules also have a typical energy scale, maybe 10 to the minus 3 electron volts. Again, like more moving parts means that it's slower, means that it's larger. So bigger spatial scales, bigger temporal scales means lower energy scales. So that's what you get. I'm not deriving the number, but I'm trying to justify that's basically where it comes from. And from that, of course, the real world is built out of much, much heavier, complicated molecules than that. So you get even lower and lower energies once you get to long hydrocarbon chains. They can wiggle around. They have all sorts of different modes. So what I would like to do is talk about not just, so these are individual molecules. The next step would be to go from molecules to more complicated things. Alas, I have a lot things to say about more complicated things, like living organisms and complicated things where you can see structure, where you can see complexity arise and stuff like that. I have enough things that I think that it's pretty clear that I should just do a separate video on them. So I'm going to stop this one here. This is the discussion we've done on scaling. I hope that some people aren't upset because there's a whole nother discussion to have on scaling that is just much more macroscopic from the start. And, how does the heartbeat of an animal scale with its body mass or things like that? And I do want to talk about that because it is a big idea in the universe. But for this one, just to aim home, there are two main points I wanted to get across. One was this big set of hierarchies in fundamental particle physics, which some of it we understand, some of it we don't. And I didn't try very hard to explain this hierarchy. I put an electron together with a proton to get a hydrogen atom, but I didn't tell you why electrons are much lighter than the Higgs boson, or why the proton is similar to the Higgs boson within a factor of 100. But we'll get there. This is one thing I want to talk about, and this is really the other thing I wanted to talk about, the idea of the Compton wavelength and how it sets the scale for elementary particles. And then by multiplying by factors of alpha in the correct way, we go from that Compton wavelength to the size of atoms, hydrogen, but also other atoms it works for. And then you just multiply by alpha again to get the energy of the different things that can happen inside an atom. So all of these different scales, these hierarchies, are built up by making more complicated things out of simple things, and there are rules behind them. Sorry about Ant-Man not being real, but there are other things equally cool in quantum mechanics and the universe. So I hope that the reality is just as interesting as the Marvel movies.